Hi there, and welcome to our second video in this Integrated Math 1 video series. Again, my name is Dr. Prince, and I'm glad that you were able to join us for this video. Let's go ahead and take a few moments to get started with a little warm-up and see what you can do with these 6 problems. Again, if you can do some things in your head using mental math, feel free to do so and try that out, and then we'll talk about them afterwards. Alright, so let's take a look at number 1. 6 times negative 3 plus 7. So 6 times negative 3 is negative 18, plus 7 is negative 11. Again, you can try to do some of that mentally. So if you think about it step by step, 6 times negative 3 is negative 18, and then plus the 7 still. So we're negative 18 on that number line, right? Negative 18 on the number line. Which would be over here, I guess. And then we're going to go positive 7, so we're going to increase back to negative 11. And so we're going to get closer to 0 by doing that. And so we get negative 11. Alright, next one we have 2 to the 0 power. In our last video we talked about how to address natural numbers as exponents, so 1, 2, 3, 4, 5, and so on. But 0 is a little bit different. You can't really use the repeated multiplication definition for 0. We can't multiply 2 times itself 0 times. That doesn't work. And so we got to have a new definition, and it's specific just to 0. So you might remember this one. Anything to the 0 power is 1. So 2 to the 0 is 1. Let's take a look a little more in depth into why that is. So let's, for instance, take a look at the powers of 2. So we have 2 to the 4th is 16, 2 to the 3rd is 8, 2 to the 2nd power is 4. And if you notice the pattern here, every time we reduce by one exponent, by a value of 1, we're dividing by 2 over here. So let's continue this pattern. 2 to the 1st power, which we understand to be 2. And then if we go one more time to get down to that exponent of 0, we have 2 to the 0 power equals, well, if we continue to divide by 2 here, we're going to get 1. And so that's kind of how we can understand why it's 1, but really and truly it's by definition, because we've defined it to be that way, but it works really nicely with this pattern here. And if you think about looking at powers of any number, well, any number to the 1st power is going to be that number. And then if we divide by itself, you're always going to get 1. So that's why anything to the 0 power is 1. Alright, let's move on to number 3 here, 15% of 20. There's a lot of ways that you may have approached this one. One way, 15% is kind of special, and I kind of like to use this one whenever I leave a tip at a restaurant. 15% of 20. So you could separate this out and do 10% of 20 and then do 5% of 20 and add them together. So that's kind of my approach when I leave a tip. So 10% of 20. So really we're just going to divide by 10, or you can move the decimal one place and get 2. So 10% would be 2. Let's see, 5% is just going to be half of that, right? Isn't 5% half of 10%? So 10% of 20 would be 2, therefore 5% would be 1. Add them together and you get 3. So 3 is going to be 15% of 20. But that really works well with 15, but maybe it doesn't work so well with other percents. So here's another way. If I multiply the numbers involved here, so 15% and 20. So 15 and 20 are my 2 numbers involved. And then really I can even just work with 2. So if there's any zeros involved at the end, you don't really need to worry about those. Just multiply the values involved. So 15 and 2. 15 times 2 is 30, right? So 15 times 2 is 30, and then just make sense of it. I talked about number sense and reasoning in the last video. Use that to figure out that, oh, it can't be 30, right? 30 is more than 20. It can't represent 15% of it. So then just work your way back with the decimal. So move your decimal one place, okay, is 3, so not 30, but 3, 15% of 20. That makes a lot more sense. Okay, so 3 is 15% of 20. If you continue to go on, 0.3 is obviously not going to be 15% of 20. There are so many different ways to approach this problem. Those are just a couple, but I really like that second one of just multiplying the numbers involved. 15 and 2 is 30, and then make sense of it. Let's move on to number 4. 3 plus 2 equals 23. Obviously that is incorrect. I want to know if maybe you can fix this. How can we fix this equation so that it would work? And really that problem is in number 5 here, so it's really a duplicate problem. I apologize for that one. So let's see here. How can we fix this by inserting a number into the box here to make it actually a true statement? So, well, let's see. Maybe I can just try some different values. 3 times 2 would be 6. That's not nearly going to be enough. Let me increase that a little bit. How about 3 times 3 is not, no. 3 times 6 is 18 plus 2 is 20. Getting closer. 3 times 7 is 21 plus 2 equals 23. So 7 is the value that makes that statement true. And then lastly, number 6 here, what is the next number in the pattern below? We have 3, 11, 19, and 27. So if you think about it, if you kind of reason through, again, number sense, it looks like we're adding 8 each time here. So if you go on to the next term, you would add 8 to 27, and you would get a next value of 35. So 35 would be the next term. Again, in the last video we talked about this idea of repeated addition. And that's what's happening here. We're repeatedly adding 8 every term. And that's the idea of repeated addition. We're going to call that slope later on. We'll call it a common difference later on. But just think of that idea right now as just being a repeated addition in this sequence. This sequence of numbers in this pattern. Okay? So let's move on to today's lesson, which we have a goal of describing and using key features of graphs to understand real-world contexts and situations. So we're going to talk about these key features, how to find them in the graph, how they describe the real world, and things like that. So let's begin with matching up, and we're going to do a lot of matching today. So we're going to match up these situations here with their graph, and I hope you can see all the numbers involved here. But we have 3 situations. A says, it was a beautiful sunny day from sunrise to sunset, not a cloud in the sky. B, the day started off foggy, but eventually the fog lifted and it was sunny the rest of the day. And then C, it was a pretty gloomy day. The morning fog never really lifted. So we're going to try to match these situations with these graphs. And let me kind of show you these graphs here. So basically these graphs, it says WM squared, and that's the solar radiation. Basically it's how much sun these solar panels are absorbing. So basically it's how much sun is out. And so you can see the 3 graphs here. That's the vertical axis, is that the amount of sun in this context here. And then the hour, so it goes from, it's military time, so 0 all the way to what would be 24, which is also, again, 0 of the next day. And so, so take a moment and see if you can match these graphs with their contexts. All right, so hopefully you noticed one thing that we've got to be really careful about, and that is the scale. So the scale here is 100, so it goes up 100, 200, 300, 400, 500, 600, 700, 800. This one, same thing, right? But hopefully you notice the one up here. The scale is 25 on the vertical axis. So it only actually goes up to 225 is the maximum value there that we can see in the scale. So we can't just compare these graphs as if they're all the same, we've got to pay attention to the scale. And that's a really important habit of mind to have as you analyze graphs and compare them. So let's see here. It was a beautiful sunny day from sunrise to sunset, not a cloud in the sky. So we would imagine that that would be the graph that included the highest values of sun throughout the entire day. And so hopefully you saw that when comparing them, that this graph here, it continued to rise throughout the day, and then it began to fall. And so if we think about this one, it started out pretty flat, and then it started to increase, and that's one of our key words for today is when a graph increases, it's increasing, and then when we hit about 12:30, maybe 1 o'clock in the afternoon, it starts to decrease. So it's increasing from maybe, 4 o'clock, 5 o'clock, all the way until around 1 o'clock in the afternoon. And then it started to decrease over time. And then it hit dusk. And so that was that situation. B, the day started off foggy, but eventually the fog lifted, and the rest of the day it was sunny. So that's going to be this one. Hopefully you recognize that in the morning it kind of stayed fairly low. The sun was kind of out, but it was fairly low around the maybe 250 mark, and then all of a sudden at 1:30 the fog lifted, and it spiked. And so if we think about some characteristics here, so it was increasing, and then it kind of leveled off, and it did not increase at all here. It stayed flat. And then it increased, then it decreased, then it increased, then it decreased, and then it increased all the way up here to what we call the maximum value. Same thing over here. This was a maximum value. So it reached the maximum value of our graph here, and then maybe decreased just a tiny bit there, but then it decreased a lot here. And then increased a little bit, then decreased on down into nighttime. So we think about these words here: increasing, decreasing, maximum. We could also think about minimums. We don't really have an overall minimum per se that we can really point out in these graphs, but we can talk about relative maximums and minimums. So the overall maximums and minimums we've been talking about, right? This is the overall max. This one right here, though, look at this one here. Is this the overall max during this day? No. But in this little zone here, in this little region of the graph, it is the maximum, right? So this is what we call a relative max. So any little peaks or valleys in your graph might be a relative max or min. So this one's a relative maximum, whereas this one, it goes down and then it increases. So this one would be a relative min, as well as this one here. Those are relative minimums. And so we have maximums and minimums, but we also have absolute versus just relative maxes and mins. So some good characteristics there. All right, so the last one is it was pretty gloomy day. The morning fog never lifted. Obviously, we only have one graph left, but the maximum of that graph was around, maybe 250 or so, which is actually right here on this graph. Which was kind of when it was foggy on this one, and so it makes sense that this one never went beyond 225, 250, somewhere in there, and then of course it went down from there and hit nighttime. So it's the scale on that one that really speaks to why that one is the one that was kind of gloomy all day. So be really careful with the scale when you see certain graphs. All right, so that was a great activity to kind of look at some characteristics. Now let's focus on how can we take maybe a real context situation and think about what the graph would look like. In this situation, we have a number of different things that we're pouring water into. So we're pouring water into these at a constant rate. So we imagine having a hose with water coming out of it, and the rate at which it's coming out and into these is constant. And what we want to do is think about how is the height of the water changing over time with respect to height. So it's not with respect to time, but to height. So how does the volume and the height interact with one another? So as the volume increases, so really it is kind of time since we're at a constant rate. So as the volume increases, so as this water continues to be poured in, how does the overall height change in terms of the water level in these different glasses or vases that we're putting into? So take a moment and see if you can kind of think through some of these and what they would match up with over here in terms of the graphs. All right, so hopefully you took some time to kind of think through matching these up and were able to think about when maybe a constant rate would happen. So a constant increase such as this one here versus maybe more a fluctuating increase in the height. So let's take the ink bottle for example. The ink bottle it's got a constant width. So if we're pouring in at a constant rate, the height is going to increase at a constant rate. And so it increases at a constant rate here, but then the width gets smaller. So what do you imagine might happen if the width gets smaller? Isn't the height going to increase quicker? Because there's not as much volume there to take up. So it's going to be a constant rate, and then it's going to still increase in height, but at a slower rate. And it's not going to be constant because it's getting skinnier and skinnier. And then we end, though, with a constant width, which is then going to be a constant rate. So if you look at G, so G increases at a constant rate to begin with, but then you can kind of see the curvature here. As this width here decreases, it's going to slowly increase in terms of how quickly it's going up. So the rate is going to increase in terms of the height. And then at the very end, you can kind of barely see it here, there's a constant increase, constant rate there. Let's take the flask up next, and it starts out with a really wide base and then gets narrower over time. It's going to kind of mirror what we saw here in the ink bottle, where it's going to kind of slowly increase over time. And so that one's going to be, let's see, flask is I. So that's the evaporating flask. Conical flask is D. So yeah, so it's going to look like that overall shape that I talked about a second ago, where it kind of is slowly increasing in terms of the rate at which it goes. Okay, so then next we have the vase. The vase starts out at kind of a narrow base and then gets really skinny, but then kind of opens up. And so if we look at E, so it's really kind of skinny, but then it gets even narrower. So the rate's going to get slower, and then the rate's going to increase because the narrower it is, the quicker it's going to increase. It gets really narrow in here, so it's going to increase really quickly, but then it opens up at the top, and so it's going to kind of slow down in terms of the increase in height. All right, up next we have the flask, which is kind of a different shape here, more circular in nature, and so it's going to get wider, but then it's going to get narrow. So if you think about that, it's going to start out, and the height is going to get, it's going to get wider, so the height's going to be kind of slower over time here, and then as it gets narrow, the height's going to increase really quickly. But keep in mind that the height's always going to increase because we're pouring in the water. It's just going to be at the rate at which it increases. So it's going to kind of increase pretty quickly there at the bottom because it's still pretty narrow. And then as it opens up, the rate's going to slow down, slow down, and then it's going to increase as that that circle kind of closes up again there. All right, the bucket starts out narrow and opens up. So if you imagine, it should get the height's still going to increase, but it should be at a slower and slower and slower rate as it does that because it's widening up. And so A does that. A starts out increasing at a pretty quick rate, but then it kind of tapers off as it goes. And then lastly, the funnel is let's see, B. So let's see, starts at a narrow. So it's going to be, but look at it, the width stays constant here. So therefore the height as the height increases, it should be at a constant rate. And so again, that's why it's going to be D. Oh, sorry, B. Yeah, B. So it's got a constant rate here. Yeah, and then it opens up, so it increases, but it's going to be slower and slower as you go. One thing I failed to mention earlier is that there's a few of these that actually don't have a match. Those are H and C, and I think there's one more. We'll get to that here in just a moment. So those are the matching up there, if you didn't kind of follow the video through with that. And then there are three more. So these three here. So H kind of goes a little bit slower, then it increases, then it slows, then it increases, and that's going to be this vase here. It starts out pretty quick, but then it slows down, and then it increases again at the top there. And then T goes along with C, because they're both the same width at the bottom here and at the top. So they're going to have a constant rate to begin with and a constant rate at the end, and so you can see that there, constant rate on both of those. All right, and then the last one here, let's see, this one should also be a constant rate to begin with, but a slower constant rate, or a smaller constant rate afterwards, larger constant rate afterwards, because it's skinnier. So that's going to be F. So we have a constant rate here, and then it's going to increase even quicker because it's narrow at the top, and so that's why we get F for that one. All right, so we've talked about a number of things today in terms of the graphs and connecting it to one another. We've talked about increasing and decreasing. We've talked about a constant rate. We've talked about maximums and minimums as well as relative maximums and minimums. We've talked about steepness or slope and how that's really rate of change is what that is. And how that changes based on the situation and in that case the width of the vase. We also talked about looking out for the scale and how that can be important and kind of be sometimes pushing you in the wrong direction. And it can be deceiving in terms of the graph. Also know your units. What are my units involved in this graph, and how does that play into things? We also connected real-world quantities with their graphs, talking about how those vases were filling up with water and how that changed the graph involved, as well as the one with measuring the sunlight during the day. So our goal today, again, was to describe these key features of graphs to understand real-world situations, and hopefully we were able to accomplish that today. And in our next video, we're going to talk about functions and what a function is, how do we analyze it, and those kinds of things. So I hope you'll join me for the next video, and we'll see you then.